But maybe he's kind of doing both at the same time. I don't know. Maybe it's something feels different about this method than what I'm used to. Not what I'm used to, but like when I haven't used Eisenbud or I've used like Jacobson. I think Jacobson, Oxford Jacobson. But my favorite algebra book. Pretty dense though. Read that hard book down there. 2 parts. Yeah, basic algebra 1.
I have looked at it and considered actually getting it.
A couple of extra copies. Paperback, paper. I love that. One thing I loved about that book the most is that are those books. Is that book really invites people to like, come and tell you that when you have a book that says basic algebra 1, and you're sitting in a cafe, people will like voluntarily, they'll volunteer to help you. And I loved it. I'm gonna be like, yes, please. Right. They'd be like, I don't remember this. Like, yeah.
That's why I'm reviewing it. It's this new math thing.
You learn this. Oh shit.
How many parents that could just be like
Parents?
Yeah, like if a parent walked up and was like, "Are you working on this?" And I just told them that I was high school now.
Mm-hmm.
High school, yeah.
Might work on a few. I mean, it really is like, I mean, of course, people don't know anything about math. So, I mean, they think math is adding numbers together and stuff. And usually they're very shocked, in my experience, at the idea that people still like research mathematics. Like that whole idea is really strange.
My friends all ask if we just like bigger and bigger numbers.
Yeah. I hope you say yes.
I was gonna say,
I've got this great professor who's really good at really big.
He's amazing.
And I go, what to call genuses? Well, I could you can use a few numbers, and then I did an even bigger one by adding 1.
yeah, they figure out all pi.
All of them.
Well, I know
That would be impressive.
0, 1.
I don't know, yeah. How do you know each digit is supposed to.
Okay, so I was supposed to copy down some things. I think I don't think actually, I think I might have everything I need to remember from last time. But let's see. So we needed to prove this. So there was another thing about this, about being a Jacobson, right? Which is pretty important. And well, I mean, it's essentially this, what he calls, I mean, this Nullstellensatz general form doesn't look anything like a Nullstellensatz, I would say, if you look at Eisenbud, that you would see in a normal, well, you see it described in a normal setting. So I'll try to make that, I'll try to point out precisely where this goes to this sort of usual form, where we're using that. But this is very much like, to me, reminiscent of sort of a Zariski statement. Okay, but before we get to that, let's prove this trick, so-called trick. And I had started, but I didn't get very far. So let me just start over. So recall R being Jacobson means that every prime ideal or every is going to be the intersection of maximal ideals. And so that's kind of an abstract condition, whereas B is I guess, a more concrete, certainly the one that we use when we look at when we prove Null-Stellensatz. So B is a sort of a practical way of deciding whether a given ring is a Jacobson ring. As we'll see. All right. So for this, I said that we should note that S is Jacobson. Because R is Jacobson. Certainly, that's some quotients, even by non-prime ideals. And of course, S is an integral domain. Okay. So that implies that 0, because it's an integral domain, the ideal, which is a 0, is prime. And so in particular, because it's Jacobson, we can look at this over all maximal ideals. And intersect all of them. So we'll get this equation. Now, if I look at the spec of S localized at B, where B is a non-zero element of this quotient ring, this ring S, this is going to equal, well, because I'm localizing, we have this statement that this is all prime ideals in S, for which B is not a prime ideal. There's this relationship between ideals not intersecting the localizing set and prime ideals of the localization. Okay, so if this is a field, and what is this? Then on the other hand, this is going to just consist of one element, which is 0. So that implies that B is in every prime ideal as non-zero. Been with me? Okay, but this implies that 0 is in S. Why? Because otherwise, I mean, again, maybe just looking at this. I mean, P is in every B is in every prime ideal, so B is in all of these maxima. So if this is not maximal, then this intersection does not have 0 in it, which means B is in that intersection, which means B is in 0, but B is non-zero. So S is P. If 0 is maximal, then S is a P. For integral. Okay, so that's A implies B. Now what about the other way? So we've got this funky condition. We want to verify that that implies that any prime ideal is intersection of the maximum ideals containing. Okay, so let's assume that we have some and we'll take the I to equal the intersection of all the maximal ideals containing Q. Okay. So of course, if Q is always equal to I, then we're Jacobson. So we'll assume otherwise. We'll assume that Q minus I has an element in it, which, or sorry, minus Q is an element, which we'll call B. Okay. So now let P probably should use capital P. That's the notation of the P be maximal with respect to the following condition. Well, that Q is contained in P and B is not in P. Is it okay? Can I find it? Is someone okay with it? Good. Okay. So let's make a couple of, now we're going to make a couple of observations about P. So observe, P is not maximal. INS. Pardon me, S, what's S? R. Because if it were, then, you know, B is not in here, but B is in I. So if P were maximal, then it would be included in this intersection, and then B would not be in I.
I have a possibly stupid question.
Huh?
I have a possibly stupid question.
Sorry.
Is capital Q different from lowercase q?
Yeah, just my notes are all over the place. Thank you. It's not. It's a good question. Thank you. Okay. So it's not a maximal ideal. So in particular, this implies that if I take R over P, this is not a field. But on the other hand, P is maximal. So where is P? Why were you guys thinking that? I mean, I guess I'm going to go backwards. Why are you guys thinking that this makes sense? I asked.
Are we trying to?
So this, all I'm saying is I looked around when I said this because I've got this, you know, droning, monotonous voice. And I just wanted to I said, this makes sense to everybody? Like, why is this? Why can we say this? Everyone's like, yeah, it's fine. So why is it fine? Like, what is happening in your brain when I say that? I know what happens in my brain. I don't know what happens in your brain. Huh? Huh?
It's a Zorn.
Okay, that's happening in your brain. Okay, that's just reasonable. Well, here's what happens in my brain with this. Is when I see this, I mean, I think B not in P I think about like this kind of a statement. I mean, honestly, what I'm thinking about here is I'm thinking, you know, this condition, Q is contained in P, means that I can think of P as a prime, as some ideal in R mod Q. And then I can think this is like saying, well, it's in R mod Q localized at B. So I want to say, but P is maximal. With respect to this condition. Or was it? Sorry. This condition means it's a maximal ideal. I mean, when you put it in there in S over Q, which should be lowercase q. But if I quotient, then I can quotient this ring. Look at it this way. This is a field. I quotient by maximal ideal, I get a field. So this is contradicting B. Saying I've found some prime ideal P so that when I invert some element, I get a field, but S over but P is not, this is not a field. So that would contradict B. So and what led to the contradiction, of course, was that we assumed that I is not Q.
Scroll back up to
That statement, yeah.
So stack of the localization at B of S primes such that B is not in B. Could we have skipped the step about like the argument about S over S mod Q localized at B and just gone to S mod P localized at B and said, well, it's maximal with respect to that property?
Well, I guess what I wanted to convince you that S mod P localized at B is a field.
Right.
So I'm not sure how I would, I mean, why would that be convinced? So how did you, I mean, I'm just saying that the way I see it, the reason it's a field is because I know P is a maximal ideal inside of some section of S mod Q.
Right. So would P be maximal in the localization of S at B?
What's S? There is no S. I should have said R.
What is, oh, okay.
I did say R. No, I didn't. I should say R.
So is R S?
No, R is maybe the R. No, S is R mod P. S is R mod P.
Okay.
The R mod Q is intermediary to get to the P.
Okay, so then
I'm sorry. I'm sorry.
So then forgetting about the S then, if it's a spec of R localized at B, would P be maximal in that, or P localized at B, or P R times R
spec of R mod. Yes, it is a maximal ideal in that ring. That's true.
So then we could.
So you can say that. Yeah, you could say that.
Just wanted to make sure.
Yes. No, that's valid. Yeah, I understand what you're saying now. Yeah, that's fine. I guess what I wanted to do was make sure that we saw both of these conditions in this sort of in one ring. That's what I was trying to go at. But you're right. If it's maximal once we localize, then it's maximal. Yeah, it's okay. All right, so we've got this nice characterization. And now we want to just jump at Nullstellensatz. So let's do that. So I think it's actually worth doing the following thing, so I'll do it. So I'm going to put this statement here. And we're going to need both of these. We're going to need what we just had. We're going to need this lemma. So I will just bring down. We're also going to need something we did when we did the going up theorem. Week 6. So this was this corollary. I don't think I have it here. Sorry. Maybe I don't have this. I'm going to bring this over. Okay, so let me just write down recall for you. So there's this other corollary that we had. Said the following thing, which said that if S is a finite, pardon me, an integral extension, then and P is, I'm just going to write the part that is relevant for us. And P is prime S. Then E is maximal if and only if its intersection with R is a maximal ideal of R. This came from this statement that if we had an integral extension and one was a field and the other was a field. And so you'll see that this is going to be used essentially in this second statement. What we in this here. So maybe who knows Nullstellensatz? Like, who's seen Nullstellensatz? So how is this what you saw before? No. Okay, so what is different? What do you notice that is very different about the statement? Huh?
Do you want alphabetical or?
Well,
order?
what strikes you? Okay, so in the Nullstellensatz you have seen. What is kind of what? How do you understand? What is the kind of paraphrasing? Radicals. Okay, under what conditions?
Algebraic.
That's what I'm going. There's some statement about the field being algebraic. And you'll look here and you'll see there's no statement at all about any algebraic. This is a statement that's just completely general. There is, I mean, of course, you have some Jacobson ring, but there is a statement about field, namely finite extension, and that will come into play. But yeah, that's sort of missing. But in that sense, this is much more general, and we can probably say do more with this. I'm not sure exactly what. Tell me. Okay, so let's prove this this mysterious theorem, and then we'll see how this relates to our. So I don't know. I would say that if, not to get too far ahead, the usual way you think of Nullstellensatz, that's fine. I think that's a sophisticated way is to look at radical ideals and have this correspondence between algebraic sets. That's a very sophisticated way, but you can always also do something really, really elementary, which is like the baby Nullstellensatz version, which is to say, if I have an ideal, there's a point in its zero locus. Like that's kind of like a key thing, right? That any set of polynomials will vanish somewhere. As long as it doesn't generate the whole ring. As long as one's not it. That's kind of geometrically what we want.
Also, see a lot more where algebraic closure.
Yeah, exactly.
Here, where it's still.
It's a mystery.
In anticipation.
Yeah. Yeah. Now let's see. We'll see how that is Zariski's lemma. So I think it actually is in basically the same idea. All right. Okay, so let's prove this this mysterious thing. So proof is kind of long and involved, but I may stumble a little, so keep me honest or don't. That's up to you. So what I'm following his notes. I'm trying to kind of paraphrase sometimes, but okay. Let's take a look at the special. He starts with a special case. R field. And S. So let me just, the arc of this proof is to do it's an induction proof. And it's an induction proof on the number of generators. We have that S is finitely generated over R. So we do kind of what we did with integral extensions. The first thing we did with integral extensions, we looked at like when we have one generator, right? Finite generators later, but we do one generator. So this is kind of a similar thing, but an even more special version than just one generator is R is actually a field, and we have one generator. S, oops. Certainly that's a finitely generated R algebra. Okay. So then he takes this part first, and he talks about that first. So in this case. So for that part, okay, well, we have N. This isn't too bad. You guys can tell me about this. N is an S. What is this? It's maximal ideal inside of R of X. So what is it?
I want to say.
Do what you want. Do what you want.
I want to say it's X minus R or something.
Oh my God! Don't do what you want.
But I know R is not necessarily on great.
Yeah, forget it. Okay, sorry if I brought it up. This is right now we're out of that context. We're just proving things. We don't have that assumption. But what we do know is we've got a polynomial ring over with coefficients of field. It's principal ideal. It's a PID. This is like your main PID. No, well, I don't know, integers, I guess. I mean, okay, but the PID that you really are going to be interested in as a geometer is going to be like, yeah, F of R of X or R is a field, right? So, but in general, this is a PID. So we have that there's some irreducible polynomial F of X for which this is principal. Okay. Okay. Well, so what do we want to conclude? Well, but then if I take N intersect R, this is just 0, right? Which is certainly maximal in my field. So what do I want? I want to conclude that this is maximal, okay? Maximal. And of course, and we all know that S over N is algebraic and finite, degree of F. Everyone's okay with this? I mean, come on, you all took your quals, right? Okay. Okay, so this is our special case. Done with the special case. Now let's go to the other to another special case, which is our base case. Maybe we'll call it base case. One generator. This is the only case I'll really do. The general case is just repeatedly. Okay. So we'll assume you have one generator. So by T over R. Okay. So what we want to do is, what do we want to prove? We want to prove that S, well, we have S is finitely generated, it's generated by one element. We want to prove that S is a Jacobson.
No longer assuming that R is.
No longer assuming R is a field. We're just assuming that S is generated by T over R. I believe that's fine, yes. Yes, we're okay. Basically, we'll get to the field case, I think. Yeah, it's fine. Okay. Why? Induction. Base case. Should be. No. 1T, we're doing base case. The induction is on the number of generators. The number of generators. All right. So we want to prove it's a Jacobson ring, and we're not going to prove that every prime ideal is the intersection of maximal ideals. That's insane. So we're going to use this trick and our lemma, and we're going to prove this statement. So we're going to prove, so we'll prove lemma property 420b. This case. Okay, so now I want to say, without loss of generality, we can assume that P is 0 and R is continuous. So why can we assume if P is 0? We can just quotient if it's not. This is all, I mean, R.
Essentially, we're just assuming that R is an integral.
Yes, we can assume R. Well, essentially, this property here for S. It's a little bit ugly because I've got it. I think I have different S's here. I think my S is, I want to prove this for S. It's kind of not very good. Actually, this notation is not very good. All right. Anyway, we want to prove the property for S here, that S is a Jacobson ring. But the point is that we don't, in that property, we don't need, we can just quotient by P. So we'll just take P and everything is, yeah, it's fine. So what are we going to do? We assume that P0 of R is, and there exists a B in S with S of B. So what we want to conclude that if this happens, then that S is a field. We want to. So I want to conclude S is a field. All right. Yeah, I didn't notice that before, but that's notation. Too many S's. All right. Okay, so now note, let's get started on proving this. So note that S, of course, is isomorphic to R of X over Q, some ideal Q. I mean, I'm assuming it's an integral domain because, as was, I'm assuming it's an integral domain because P is 0. So for Q in spec R of X. Do you guys agree? Tell me when I lose you. S is an integral domain. So I'm assuming without loss of generality, if you believe this, yeah, then I can assume. Everyone else okay? So it's, and why this is true, I mean, again, we're in the base case. So it's generated by T, and this is just our T essentially. When you look in the residues. Okay. Okay, so we want to prove a few things about this situation. First, note a Q can't be 0. Why? Well, so this is because otherwise, when I take R, then S is just R of X. I'm going to localize one element, one polynomial of R of X is a field. This is a weird thing to think. I don't know if you've ever thought about it. If you think of like polynomials and you're just thinking of rational functions where you only allow one polynomial in the denominator, that to be a field would seem a little strange. It is. This will imply, so this being a field, this will imply, because R is an integral domain here, it's contained in S. Again, this statement is also sort of quotienting by P. Quotient by P intersect R. So I do want to say, so this, without loss of generality, you do kind of, you're using that you can quotient by everything. So you get into domains. And so is this guy. Well, this is kind of a silly thing to say, but it's anyway. So where K, the field of fractions, quotient ring algorithms. Fractions. Why is that true? Tell me why.
Sorry, so we're saying that this would also then be a field.
Actually, kind of.
You have an inverse for X for any polynomial, then an inverse for K gives you an inverse for everything else.
Well, it gives you an inverse, I would say, for the constant polynomial. Right. I mean, in some sense, these would have to be the same ring, right? Because you're saying that it's a field, so all of the constants have inverses. Constants are self-applied. So the K is already in here. So I'm just saying this is a field. Yeah. But then, by the lemma and the special case, so this, what I'm saying here now, we're in the special case, right? We're in the special case where we have now a field and we're inverting one guy. Right. So, oops, special case. K of X is a field. Now that doesn't work. So this is all this to say, no, this, you can't have Q equal to 0. Q is 0, we have okay. So Q is not 0. And in particular, that means there's an element, a non-trivial element in Q. So, but again, we want to assume, we want to be in this case. So we're going to assume we have some element B in S that localizes to it, localizes us to a field. So we have and B S. So the S field. Okay, so maybe I'll rewrite this slightly different. This is equal to okay, well, it's R over Q, R of X over Q. So B, but this is also going to be K of X for Q times K of X. It's Q times K of X. And again, if you have the point is we are assuming this is a field, so the constants are going to be invertible, so we can represent it this way. But of course, also, and indeed, moreover, a finite field extension. I mean, because we know Q is non-zero. Extension. Because Q is non-zero, there has to be a polynomial in there. So we get a finite. Okay, so what can we do with that? We still haven't, I mean, we haven't proven that R of X over Q is a field, so which is what we want, but that S is a field to show this Jacobson condition. And so for that, we do the following thing. So because we have a finite field extension, we know that every element in this finite field extension is algebraic over K. So we can choose a P of X, Q, non-zero P of X in Q, such that writing out this polynomial. So here it's not monic necessarily. I mean, it's kind of, we're using the fact that we've gone to field, so we have to have some potential fractions, but we can clear denominators and still write this out. And P of T is 0. So we want to say that T is algebraic, certainly. And also B is algebraic. I mean, B is also in this finite field extension. And choose Q of X. M. So that Q of B is 0. And we can also do this in such a way. Okay, so here we need to say why, but and QI are in R. We can do this so that QI is also in R. The reason for that is because, well, let's see here. Well, I guess there's nothing really to say here. I mean, what am I saying? This is a finite field extension of what? Of K. So I don't think this is, I wanted to say something, but I don't think so.
The PI.
Yeah. Yeah, exactly. So I was getting a little ahead of myself. I think right now I don't have to say. So yeah, we'll say both of these PI and QI. I do want to say something in a second, but I haven't quite got there. So multiply this Q polynomial by 1 over QM or Q naught, pardon me, Q naught to the BM, and observe then that B inverse is integral over not R necessarily, but R localized at Q. I had to divide by Q. I could have done the same thing over here and said that T is integral over R localized at Pn. Okay, I think I've got what I need. To say the following, which is to say, yeah, please.
Why for B did we divide through by Q naught, but for T we divided through by N? Like, is that just a choice?
Well, because what I want to do is I want to say, if I divide through by Pn here, I get that T satisfies a monic polynomial. If I do here, I need to divide by Q naught because what I want is I don't want B. I want to say that B inverse satisfies a monic polynomial. So that's why. So in particular, what I want to say is the following thing. So thus, when I look at these two elements, T and B inverse, as elements of S localized at B and localized at Q naught, I guess we could do it at both, sorry, not at B, pardon me, at Qn times Q naught, Pn times Q naught. So I localize this one element. These are both are integral over, of course, R localized at the same element. Okay. Okay, but then the point is that, okay, but here's the punchline: S, B inverse is generated by these two elements. Right? S is generated by T, and when I localize, I'm generating by B inverse. So that implies, by our previous results on integral extensions, that S of B inverse is integral over R for this guy. And then what do we get from that, guys? Now I'll see how many people are following this insane argument. What do we get from that? So we've got an integral extension over R localized at this one element, And what is this integral extension? Where we started with? It's a field.
So that means
It's that
R P dot Q N inverse.
that's right. That's right. That was our old corollary that I cited. So this guy is a field. But now we have that same 420B property because R was assumed to be Jacobson to say that then R is a field. This is a field. Good. By our special, or by just the fact that we have an integral extension over our field fractions.
It's really focused everywhere.
It's a lot. So it's a lot. So this is the now, yeah, and you can look at the claim on maximal ideals and work that out, and then the rest is induction. So I'm just, there's like maybe 3 or 4 more lines. Read them in Eisenberg. It's just, repeat with induction. Okay, so next time, what we'll do is we'll apply this and we'll see how to connect this general Nullstellensatz with, I think, more familiar notion of what we think of as Nullstellensatz. We'll do that Friday. Yeah, stop. I don't
Flip the indices on your
probably.
non-UN
Probably.
there.
Yeah, I think the last couple. I can't even read my own writing, so. Thank you. I did want to ask you. So I was told that nobody understands my drawings. Is it true? Like when I draw sketch these pictures, like do they make sense to you guys to some degree? You can take them as like heuristic things, right? I mean, but actually there's like usually there's a mental space there.
Right. I usually interpret them as there's something like precise going on here, but it's above my pay grade, as it were. And I'm just like, all right, I kind of get it.
I mean, I wanted to emphasize this. There is this equivalence of categories between rings, commutative rings, and things called affine schemes. But those so if you want, you can think it for when you have like no potence, you can think of these as this being the functor spec. Right? So you get a topological space for a ring. For a homomorphism, you get a map, a continuous map of topological spaces. So what I want to say is if you are in that camp where you're like, I don't know what that is supposed to mean, that's what it means. I'm just taking these rings, I'm looking at that functor and I'm drawing pictures of the spaces. Okay, and then there's subspaces and so on within that. But I'm trying to say, okay, here's the algebraic picture. What does it look like when we apply that one? What are all these things? So just take it as that if it's like confusing. Okay, and if you want, just tell me to be more detailed.
What is an affine scheme?
What is an affine scheme?
Yeah.
It's okay. I mean, it's a locally ringed space, right? Okay. So it's got this sheaf on it. But the underlying set is just spec. So the underlying topology, it's just topology, the Zariski topology. Both sets are I for ideals. So there's some topological space, but the scheme part is that you also have this sheaf of rings, the structure.
I see.
And so when you don't have, you can have some nilpotence and things like that. So you need to kind of, in order for this to be equivalence categories, you need to say, okay, well, it's not just there's the ring of functions on it, and maybe some of the power is here. Like that. Gotcha.
Will Rena talk about that stuff next?
She should, yeah, I think she'll